Hello everyone and welcome to this edition of CSCI 343 Fundamentals of Data Science. So yesterday we had a really awesome live class meeting and the Zoom recording did not capture the audio. Why? Who knows? Anyway, so today we're going to recap the material that we talked about then. It'll be a little less or a little more boring actually because it was an interactive exercise. So humor me. All right. So, moving right along. So, as we've talked about before, the human brain is outstanding at seeing patterns. We can look at things and very quickly figure out certain types of patterns. There are certain kinds of information that we're actually quite sensitive to. So, let's play a little game where we take advantage of you, the human computer, and see if you can figure out some patterns. So, several years back, Time Magazine did an interesting photo series called The Hungry Planet. And it was a really cool concept. What they did is they went to families in different countries and had them pose in front of a week's worth of groceries. And so our exercise in class was to look at each one of these and name what we saw in the photographs. So in this one, usually the first thing people name are of course, the pizzas. And then, there's some other breads and meat and drinks and those kind of things. And we continued this exercise going through places like Japan and Chad and Italy and Mexico and Ecuador and Mongolia and so on and so forth, and Britain, Egypt, Australia. And of course, this one's my favorite. And the reason it's my favorite is because the kid there, definitely like your archetype of teenage angst. And I like that. This is fun. So anyway, the point of this whole exercise was I was tricking you into doing statistics. If you go back and we looked at the list of all of the things that we saw and that we named while we were going through each of these photographs, you always named them in a certain order. Which leads us to this nifty question. What was the first statistic you ever learned to compute? It's a tricky question. A lot of people give different answers. Some people was like, well, I learned, that I had X amount of time to do something, or I had X amount of cookie left, or something like that. And you're all sort of in the ballpark of where I'm going. Probably the first real statistical analysis you ever performed was counting. And at home, I've got a toddler right now who's loving up some Sesame Street and other stuff. And so I'm getting a refresher on how to count things. Anyway, so one of the cool things is just by counting how much of something is available or how much of something is in a photograph or in your refrigerator or in your data set, you can tell a lot about what's important, what's plentiful, a lot of different things. And can be a very useful statistic. For instance, just looking at word counts can sometimes tell you a little bit in a very rudimentary way about what's important to people. For instance, back when we did this class in person, I'd give out a paper survey that would ask some questions. And one of those questions was, why are you in this class? And then after, the survey was turned in, I would give those papers to the class TA, and that TA would be an awesome sport and type up those things into a spreadsheet where I could actually look at each of the words that people used. And if we look at the frequency of words used in the response to this question, we see some patterns. Now, I've whited out the columns for data and science because, well, this is a data science class, so obviously we're going to be talking about those things. And the next things that you see are, it's interesting, it's a class, well, you got to take classes. Learn, Python, seemed elective, more topic course, CSCI, which is the course prefix, and needed. So overall, people were interested in data science, they wanted to learn about Python, and later on down the line, they needed an extra elective, which, that's fair enough. Now, we didn't perform any rigorous statistics here, but just looking at the frequency of word use, we can see that some patterns are emerging. That people were interested in the topic, that they're interested in Python, and that they need electives. Similarly, we also asked the question, what do you want to get out of this class? And again, data and science, we expect those to kind of show up a lot in here because, well, it's a data science class. And just looking at word counts, we see, people want to learn. They want knowledge. They want Python and more experience. And, it kind of trails off after that. So a lot of the things that, you'd sort of expect people to be interested in about the class show up in terms of word frequency. So just by looking at the frequency of these words being used in the responses, we can figure out a little bit in sort of a very basic way about what the people answering these questions think is important. Now, that's just by counting stuff. Now, a lot of the research that people do and a lot of the data analysis people do is more complicated than that. But in the end, all of our statistical analyses start with counting how many things we're looking at. Just a straight count, the n, the number of things that we're analyzing, are going to come into play just about every statistical analysis that we do in some form or another. And it can often tell us something interesting just by looking at that from sort of a starting point. Now, as we've talked about in here plenty of times, and believe me, you'll hear more of it, I work with virtual reality. And one of the things that I do is I like to study how people perceive the three-dimensional space that they're operating in. And one really cool way that we do that is using a technique called blind walking. It's really, really cool. It doesn't even sound like it should work. But what it is you have people look at an object. And when they feel like they've got a good sense of where it's located, you blindfold them or have them close their eyes or something. And then you have them walk to where they believe the object was. And then you measure where they walked to. You measure how far they walked. And turns out this is a really good estimate of how people perceive where objects are in the space around them. And if you think about it, it kind of makes sense because walking without vision is sort of a survival skill. It's something that we kind of need to do, so you'd expect us to be good at it. For instance, if you had to keep eye contact with whatever you were walking to while you were walking to it, chances are, we wouldn't survive very long because then you couldn't attend to your surroundings and look out for predators and obstacles and other things like that. So one of the first things I like to do when I run a study, I collect some data, is just to plot a histogram, a count of how many responses fell into certain ranges. And here are examples of responses from real, actual studies that I've done in the past. The first one here is a blind walking study, or rather this one to your left is a blind walking study where we're looking at people walking in virtual reality. And then on the other side, on your right, we have another plot of how people walked in the real world. Now, these are essentially just counts of how many responses fell into each one of these bins. And that's pretty cool because it can tell us some really interesting stuff. We can immediately look at this and we can see, oh, well, responses tended to go from about 30% up to about 100%, maybe a little bit more. Perhaps more interestingly, you can tell the average performance just by looking at the counts. For instance, we can see that, in the real world, on average, people were around the 80 to 96-ish% range, while in the virtual world, people were closer to the 64 to 70-ish% accuracy range. They're walking about 60 or 70% the distance to the target in the virtual world, while they're walking, almost 90% in the real world. And we did no high-end fancy statistics with this. We just looked at counts. Now, the interesting thing you'll probably notice is these are starting to form a very particular shape, a bell curve. This is what we call our normal distribution, and we'll talk more about normal distributions a little later on. But the cool thing is that normal distributions show up a lot. Matter of fact, they show up essentially everywhere in one form or another when you're trying to measure something. Now, some can argue with this. Like, for instance, this is from that same paper survey, how people judge their proficiency in programming. Now, this doesn't look like a normal distribution. I mean, maybe if you kind of squint your eyes and, tilt your head sideways, maybe it starts looking normal. But I would argue that it is, and I'll tell you why. When we're taking samples, we're estimating a population. And this is going to become very important for other statistical methods later on. And so we're making an approximation of how a population responds to something, or how the measured value around something, that we're examining. Now, the more samples you get, the better your representation of the thing you're trying to measure becomes. This one is just 50 samples. Well, actually less than 50 samples, probably about 40, 45 to 48. So there was less than 50 students in this class. And each one of these counts is a single student's response. So we've only got, about 40 to 50-ish responses in this, so we don't have a lot of data to work with, but we can still see already that it's starting to come close to something sort of normal-ish. But if we collect more data, this is from I think this is actually from another one of the blind walking studies, where we have several hundred responses. We're starting to see that normal curve forming. Now, it's still rough, but it's beginning to look more like one of those normal distributions. Where if we look at another study where we've got thousands of responses recorded. Now, maybe not necessarily thousands of people, but thousands of responses from dozens and dozens of people. We see something that's definitely looking like a normal distribution forming in our data. So the more data you collect, the closer you get to a normal distribution. And this is sort of what you expect to see. When you collect data and you're trying to measure a particular response or measure a particular attribute of anything, could be a population, could be data coming from a sensor, could be colors in a photograph for that matter. It doesn't matter. If you're trying to measure a specific thing, you expect to find a normal distribution in your data, which is why it's very important before you do any other analysis of your data, you should look at the raw data itself to see if it conforms to the expected distribution. Now, there's variance on the normal distribution. Now, we're going to focus primarily on the typical normal distribution in here, but there's variance of it. So knowing that it should have a normal-ish distribution to it is important. And when you don't see that, that tells you something interesting about your data. For instance, this is one of the most beautiful plots I've ever seen. I love this. These are the results of, I believe it's the 2013 Polish Matura exam. This is sort of like a high school exit / college entrance exam. So thousands and thousands of students, high school students, end up taking this test. And so you've got, this is the distribution of scores across the test. And this is beautiful because this is almost a perfect normal distribution. It's gorgeous, it's smooth, and then something weird happens. Something very strange happened right here. Now, normally when I'm doing this in person, I'm interacting with you. I'm asking questions about this. Tell me why this is weird. What's going on? And, you get a bunch of responses. Well, maybe people studied differently. Maybe it was this. Maybe it was that. Well, turns out, if you ask the right questions, you'll figure out that the minimum score to enter college is a 30. And notice there's a lot of 30s. As a matter of fact, the frequency goes way up as you approach 30. And then once you get past 30, the frequency goes way, way down. And then we end up resuming what would be our otherwise normal distribution. Now, I'm hoping you can see my mouse there as I'm going across the big screen with it. And ideally, what this test was supposed to be measuring is a student's competence. How much they learned, how much they got out of that high school education to prepare them for college. It turns out, sometimes when you collect data, you accidentally measure more than one thing. And if you see oddities like this in your distribution, that might be an indication that you accidentally measured something in addition to what you're interested in measuring. So in this example, they're interested in measuring the knowledge, the intellectual preparation of these students for college. But since 30 is the cutoff, the folks grading the test get a little more lenient, a little more lenient and a little more lenient the closer and closer you start inching towards that 30. Because who wants to deny someone their chance to go to college? Really, you know? But there comes a point where students scored so badly that there's nothing you can do about it. So what we were accidentally measuring here was one, the preparedness of the student, and two, the empathy or the sympathy, depending on the situation, of the people grading the exams. So the takeaway question here, or takeaway topic here, takeaway message, that's what I'm looking for. The takeaway message here is that always look at your raw data. Bin it like this, plot a histogram, see how many samples fall into each range, and this can tell you a lot about whether or not your data is robust enough, you have enough, whether or not you're accidentally measuring something that is in addition to what you're actually trying to measure with your study. So always look at your raw data before progressing on to other analyses. Okay, and this is where at the end of the lecture we took some questions about your upcoming challenge. Some of the questions that folks asked were about, and this is relative to Challenge 1, for those of you watching in the distant future, perhaps. So in Challenge 1, I've given you some data. It's data coming from different remote weather posts. And so one of them has gone down, and your job is to look at this data, plot the signals coming out of it, and find out which of the weather stations that we're collecting data from is no longer functioning, is delivering us random data. And you can figure out the frequency, which frequency it's the bad data is on, by a variety of means. I'm not restricting you, at least not this time. On another assignment, you have a restriction on it. But on this one, I just want you to look at your raw data, open it up, plot it. You can plot it in Excel, you can plot it in Python, Matplotlib, you can sketch it out on a piece of paper if you want, but I want you looking at that raw data. And when you look at that raw data, you'll find out which frequency has structure and which frequency is random. And then I want you to plot those and then do a line plot or do a scatter plot of the raw data and then do a line plot of the average. So that's basically how that's coming out. More or less just acquainting you with the tools that you have at your disposal for the rest of this semester. Other questions I got was, how are we demonstrating this? Well, you have to demonstrate to the class TA. You're going to screen share with the TA and execute your code. There's a couple extra steps in there, and first thing you're going to do is screen share your code with the TA. The TA is going to ask you to explain your code. So you don't have to do character per character explanation, but give the broad strokes of what this segment of code's doing, this segment of code's doing, so on and so forth. And after you've satisfied the TA's questions about the structure of your code, the TA is going to ask you to execute your code, and he's going to look at the output. The output is going to be different for each student, but our TA knows what your output should look like. And if the output fits, what we expect, what it should be for the assignment. By the way, if you have any doubts about whether or not your plot looks as it should, don't forget to consult your assignment document. There is an example in there of what the plot should roughly look like. So be sure to use the same colors, the same kind of labels for your axes, same kind of titles. It should pretty much be identical in form to the example in the assignment document, even though the wave pattern, might be different for your specific data. After that, if everything looks good, the TA is going to ask you to do something unexpected. And that unexpected thing is to break your code. So the TA is going to tell you to add or remove or edit a line of your code in such a way that it will stop it from functioning. And then you'll be asked to execute your code again. Why is he asking you to do this? Well, there's a good reason why. People are sneaky, man. Kind of like those car insurance commercials, we know a thing or two because we've seen a thing or two. And sometimes nice, clever students like yourselves decide to do less clever things and demonstrate execute a set of code that works while showing a set of code that doesn't work, but they know how to explain. So in other words, I worked on this code, I know how to explain it, but it doesn't work. So I'm going to execute someone else's. And so what we do when we break your code is we're actually proving that the code that you've explained to us is the code that you're demonstrating to us. And then after that, the TA might have a few more questions for you about your sources and things like that, something that might have caught the TA's eye. And after that, you'll be awarded points based on the day that you did your demonstration. Remember that in this class, all of the assignments are tractable. You're not graded based on how working they are. They have to work 100%. You're graded on how quickly you get them working within the submission window. Again, the submission windows typically open on a Friday and last for 6 weekdays. Weekends don't count as a penalty. So, I try to, have a little bit of wiggle room there for you guys between the first day of the submission and the second day. So, if you miss out on that first day, you got a little time there, to still get most of your points. Another question that I was asked was, how long did this take me to do? Okay, so when I did this assignment, granted, I know what I'm doing, and I've done this a lot. When I did this assignment, it took me approximately 15 to 20 minutes. Should it take you 15 or 20 minutes? For some of you, yes. For some of you who might not be like super experienced programmers or coming to us from another major, and don't code every day, this might not be a 20-minute assignment for you. It might be an hour or two, and that's okay. That's why you have a nice long window to prepare before the submission window opens. So if it takes you a long time to get these things done, don't fret. It's okay. But if you do run into problems, don't hesitate to talk to me or talk to the class TA. We're here to help you. Okay, so we're going to wrap it up right there, and this was a nice, fun, interactive lecture when we did it over video chat. Perhaps a little less interesting for those of y'all watching the after-action replay, here in our virtual environment. But again, if you have questions, please let us know, and stay happy, healthy, and safe, folks, and I'll see you in cyberspace.